The 2 terabyte memory wall. A standard transformer requires 2 terabytes of VRAM to maintain the KV cache for a 10 million token sequence. This is the hard limit of static architectures. To remember a long document, you must store every single key and value pair in physical memory. As context windows scale into the millions, the linear growth of this cache hits a hardware ceiling that no amount of quantization can solve. To scale further, we have to abandon the idea of a growing memory buffer entirely, and it starts with the memory wall. Weights as hidden states. The test time training, or TTT layer, solves the scaling problem by replacing the linear KV cache with a miniature neural network embedded inside the model itself. Instead of appending tokens to a list, the model uses each incoming token to perform a single step of gradient descent. This updates the weights of its own internal MLP. In this architecture, the context is not stored in a database, it is compressed into a set of fast weights. The paper from the Berkeley and Stanford teams shows that this allows for a constant memory footprint regardless of how long the input becomes, by treating weights as hidden states. The mechanism of real-time learning. Here is how the mechanics actually function during inference. For every new token the model receives, it creates a temporary self-supervised task, such as predicting the next character or reconstructing the current hidden representation. It then runs a mini-optimization loop inside the forward pass. This is not a fine-tune in the traditional sense. It is an inner-loop update that happens in milliseconds. By the time the model needs to generate its own response, its layers have literally learned the specific patterns of your prompt. Recent April 2026 benchmarks for the TTT-2E implementation show a 2.7 times speed increase over full attention. Transformers at 128,000 tokens, because the model avoids the quadratic overhead of looking back at every previous token. It simply looks at its updated weights, which arrive at a hidden computational cost. The compute for memory trade. The trade-off is often ignored in the marketing. While TTT eliminates the memory bottleneck, it introduces a significant compute overhead because every single token now requires a backpropagation step during inference. You are essentially paying for memory savings with increased flops. On current hardware, this can lead to higher latency for shorter prompts, making the TTT layer a specialized tool for ultra-long context rather than a universal replacement, moving us toward a dynamic weight future. The part no one wants to say. The shift from static to dynamic weights reveals a massive hardware misalignment that the industry is currently ignoring. We have spent the last decade optimizing silicon like the H100 for massive batches of frozen weight inference, yet TTT layers require a high-throughput gradient engine for every single user session. The data from the TTT-E, 2E, and in-place TTT papers suggests that the traditional memory wall is being replaced by an optimization wall. For builders, this means the competitive advantage is moving away from who has the most VRAM and toward who can run the fastest optimizer in the forward pass. If the benchmarks from April 2026 continue to hold, the era of the massive KV cache is over, but it will be replaced by a world where inference and training are computationally indistinguishable. Watch for the emergence of specialized TTT accelerators that prioritize backpropagation throughput over raw memory bandwidth. This hardware shift is the real signal under the noise. Subscribe for more